So let's discuss for a moment, what if instead of the AV node, all right, we're talking about the AV node, instead of it being a pace setter, instead of it firing early or firing quickly and causing an arrhythmia, what if it's not working as it's supposed to in a different way? So originally, right, the AV node allows for a slight delay in conduction of the signal from the atria to the ventricles. Sorry, that got a little bit sloppy there. So normally the signal goes through the atria, enters the AV node, down the bundle has bundle branches, Purkinje fibers, and you get ventricular depolarization, generally in this direction overall. And so that slight delay in the AV node allows the ventricles to fill as the atria to contract, and then the ventricles can contract and pump their full amount of stroke volume out. So the issue is, what if that delay becomes too big? Okay, and we can measure that delay because we know that the PR interval, so this is from the beginning of the P wave to the beginning of the QRS complex, but not including the QRS. So it includes atrial depolarization and the time it takes until the signal reaches the ventricles. So this distance, all right, our PR interval should be 3 to 5 small boxes, or 0.12 to 0.20 seconds in duration. That's how long it should take for the atria to depolarize and that's overall signal to get to the ventricles. But if the AV node is delaying it, the PR interval could be prolonged. So if you measure the PR interval and it's greater than 0.20 seconds, but there's nothing else wrong. So you have the P wave and a long PR interval and a P wave and a long PR interval. All right, but the QRS complex is fine. The overall rate is fine. The P waves look fine. I mean, if there's nothing else really abnormal here, it's just a long PR interval. What we do is we call this a first degree AV block or heart block. Okay, first degree, it's the least serious one. All right, it's just a slightly prolonged PRI. That is our only big issue here. And again, it's likely that the AV node, there's something going on with the AV node that's just delaying the process and deterioration of the AV node tissue with age, and something is causing it to be prolonged. Okay, but things can certainly go awry and get worse. And so if there's a first degree, there must be a second degree. The thing is, there are more than one second degree AV block. So we call these Mobitz type 1 and Mobitz type 2 second degree blocks. So second degree Mobitz type 1, second degree Mobitz type 2. Type 1, we also have another name for it. It's called Wenckebach, in case you hear that as well. So what's a second degree AV block and what's the difference between type 1 and type 2? You're clearly asking yourself these questions. So let me try to answer those. So if we look at type 1, so I'll just write type 1 here. This is type 1. You've got a P, QRS, and T. And in that first PR interval, okay, remember the PR interval is of significance in AV blocks. It might be normal, okay, but what we're going to see here is then the PR interval gets a little bit longer. And then the PR interval might get a little bit longer. And then eventually you got a P wave. And the QRS never comes, and then another P wave, QRS and T, and the pattern repeats. So you can see here the PR interval has progressively gotten longer until you have a QRS that's dropped. So we would expect a QRS somewhere in here, but we don't get it, and we call that a dropped QRS complex. And this is the hallmark of second degree type 1, a prolonging PR interval, okay? It progressively gets longer until you drop a QRS complex. All right, so it's very progressive. All right, so progressively prolonged until you drop a QRS complex. And then again, the cycle repeats. So if we looked at this, right, the P wave's normal, the QRS complex is normal, but the PR interval is the key here, right? So this is the key here. Here are the criteria for that. But the rhythm, when you're looking at the rhythm, right, this is irregular. Okay, so as that PR interval continues to get longer and you drop a QRS, the R to R interval durations are continue to get longer. So it's irregular, but there should be some sort of pattern. So maybe it is regularly irregular, because what should happen is the P to Q ratio should have some sort of regularity to it. So it might be 4 to 3. And so that's what we have here. We had 4 to 3. We had a P wave here and then a QRS complex. P wave, QRS, P wave, QRS, P wave, nothing, P wave, QRS, and it repeated. So there were 1, 2, 3, 4 P waves here, but only 3 QRS complexes. So we had a 4 to 3 that continued to repeat as that PR interval lengthening pattern also repeated. So you should have some sort of pattern there, although it can change. You might go from a 4 to 3 to a 3 to 2, where you have P wave QRS, then the P wave with a longer PR interval and a QRS, and then a dropped QRS. So it doesn't always have to be the same ratio in these sorts of instances, and you'll definitely over time see many different ones. And that's just type 1, so progressively prolonged QRS. So what about type 2? How does type 2 differ? And in second degree type 2, okay, so this first one was Wenckebach. That was the Wenckebach. In type 2, it's different. Instead of a progressively prolonged QRS complexes, they're the same. They're constant. The PR interval, so this is the key, is constant. Now the PR interval might be long. It might be normal. But it's constant when it is present, but it's not always present. You'll still have a P wave and a dropped QRS complex. And so these PR intervals are all the same length, whether they're long or short. They're all the same, but you still have a P wave with a dropped QRS complex that doesn't, right? So it doesn't come after. And so in both of these cases, right, so the AV node is getting the signal, it's passing it down, but eventually the AV node won't pass a signal or an impulse to the ventricles, and so you won't get a QRS complex. You just get the P wave. And so the difference between type 1 and type 2 is the PR interval progressively getting longer, or are they constant? But again, even in type 2, you'll have a ratio. Here we have a 3 to 2 ratio. We have 3 P waves. But only 2 QRS complexes, right? We lost 1. And then the pattern, again, it repeats. Again, it's likely to repeat at the same ratio, but over time the ratio may change as well. It may get worse. The more often you drop a QRS complex, the worse it's going to be. All right. So what is a third degree heart block or third degree AV block, and what is AV dissociation? How are they the same? How are they different? What's going on in the heart? So again, this idea that the AV node is supposed to pass the electrical activity down into the ventricles so that they can depolarize. But let's assume the AV node has completely stopped working. All right, so what's going to happen is the SA node will fire, right? The SA node is still, we're going to assume the SA node is healthy and it's firing as normal, and you get this P wave. And if you give it time, right, SA node will fire again, and it'll fire again, and it'll fire again, and it'll fire again. And the SA node will fire, right, typically at rates between 60 and 100. But normally what should happen is this impulse should go to the ventricles, and we should have seen QRS complexes, but it's not happening. And the AV node's not working. So the ventricles, assuming they're not getting any electrical impulse, will depolarize on their own. Usually, right, the idea is a rate of 20 to 40 is what the ventricles depolarize. And so you might get a depolarization, let's say right here. And that QRS complex may be wide if it's, right, the depolarization is occurring here and it has to travel all through the ventricles. If the depolarization is starting fairly high up and most of the ventricles is going to depolarize simultaneously, it may be fairly narrow as usual. But we won't get into that right now. But what we do know is we do have this depolarization of the ventricles eventually in a very slow rate. So they're not depolarizing very often. Okay, and so we're going to come out here. But assuming everything else is fine, SA node is fairly regular at a rate, we'll call this 80 beats per minute. And the QRS complex is coming in very regular, but at a rate that we'll call, it looks like a little less than 40. We'll just call it 30 beats per minute. And so we can't distinguish the difference between the two, right? Your ECG doesn't pick up the electrical activity of the atrium and ventricles separately. It can only pick up all the electrical activity at one time. And so what you would actually see on the ECG, if this was the case, would be a P wave, a P, a QRS, a T, a P, a P, a QRS, and a T. I'm trying to draw these fairly accurate, but this is what you would see. Okay, so we can see there was a P wave and nothing. There's a P, QRS, T, a P, nothing, a P, QRS, and T, a P, nothing, a P, QRS. So you look at this bottom one, this green one here, and our initial thought is, well, maybe I have a second degree heart block because I have a normal P, QRS, T, and then a P and then it's dropped, and then a P, QRS, T, and then a P and it's dropped, and certainly I could see where you would think, oh, it's a second degree heart block. Here's the problem with that. It doesn't match type 1 or type 2 second degree heart blocks. Because remember, in type 1, it should progressively get longer and then drop. What we have here is what looks like a normal PR interval, and then you have a dropped QRS. And here we have a PR interval that's long, and then a dropped QRS. And so the fact that the PR interval in this first one is not the same as this PR interval, that already tells me this is neither type 1 nor type 2 second degree heart block. Because remember, even in type 2, it's a constant PR interval. What we have here is a PR interval that is not constant. It varies throughout this rhythm. And so that doesn't match any of the heart blocks that we knew so far. But certainly the PR interval can be long, and there are dropped QRS complexes. So there's something going on with the AV node. And the next thing you want to do, like once you notice that PR interval does vary, is take a look at the regularity of the P wave. So from one P wave to the next, if I look at this, right, and we already determined this, that P wave regularity is very regular. So the P waves are firing as they should, and if you calculated the rate of the atrial depolarization and you found that it was 80, you would say, well, I know that the SA node is doing what it should. It has a beat of 80 per minute. And if you just look at the QRS complexes, and they were fairly regular, but they were slow, so that you knew the ventricles were depolarizing about 30 beats per minute with varying PR intervals, now you can start to pick out, okay, it seems to be clear that the SA node and the ventricles are not talking. The AV node has not let that impulse get through, and so the ventricles are doing their own thing, the SA node is doing its own thing. There's no talking between the two. And this then is the criteria for a third degree AV block or complete heart block, where the AV node is not working. The key here again is to look at the PR interval, notice that it's varying and not consistent throughout, and try to really pick out that it's not progressively getting longer, and that they're certainly not constant. And then take another look at the SA or the P waves to see if the SA node is firing regularly, and then look at the ventricles separately and say, well, at least are the ventricles firing regularly but slowly, and that will help you determine it's a third degree AV block.